The next thing that I am going to do now is to go in briefly into how you would interface this with hardware. Okay. So, I already sort of gave a brief picture for what we are looking at. I have a CPU. There is something that I am going to call a bus. Right? And what exactly is this bus? Is it just a collection of wires, or is it something more than that? That is actually something that we will need to spend a little bit more time on later. Okay? But for the time being, all that we care about is it is the way by which we connect things together. Okay? On the other side of the bus is some memory, right. So, for example, the board that we will be using for our testing is something called the Z board, which is based on the Xilinx Zinc processor. Okay. So, for the Z board, this is an ARM processor, okay, the same kind of ARM processor that most of you have in your mobile phones, right, a variant of that. The memory that is available to this is around 512 megabytes, quite a decent amount of memory, much more than the on-chip block RAM that is available inside the FPGA. Okay. But what that means is this is some kind of DRAM, dynamic RAM, just like you find in a PC. DRAM has a number of advantages, the main advantage being high density. You can get a significant amount of DRAM very cheaply in a small amount of space. The biggest disadvantage is high latency. Another related disadvantage is the fact that it is dynamic, meaning that it can decay and lose information if you do not keep refreshing it. Okay. So, net result is DRAM is problematic. It is not a very easy to analyze kind of memory. You can't just say I give it an address, one cycle later it gives me back the data. It does not work that way. Okay. But I can have 512 MB of DRAM, I can't even think of having 512 MB of SRAM in a design of this sort. Now, what is interesting from our point of view is we finally want to implement our FFT as some kind of a hardware accelerator, which will also then be connected to this bus. So, I am just going to call it a HA, a hardware accelerator. Okay. Now, the question is, the CPU needs to be able to communicate with everything on the right hand side. Let us say that I want to read something from a memory location. What would I do? I have an address bus and some kind of a write enable or read enable signal. If I want to read something from memory, I would put the pointer value, the address from which I want to read, onto the address bus and activate the chip enable signal. Okay. So, the address would go from here. I would also probably have some kind of a read write enable signal, probably can't read what I have written over there, and for simplicity we will think of it as there is a data write, W data, and another R data, which is the read value which is coming back from the bus. Okay. So, the interface between the CPU and the bus is there is an address, there is a read write signal, there is a W data if I want to write data into the bus, and a read data if I want to read data back from the bus. Remember, I am talking about from the bus, I am not talking about specifically memory. Okay. Why am I doing that? Because what I can then think of is that my overall memory module is mapped into something that I will call an address space. Okay. Now, an address space is essentially all the possible addresses that can be generated on the address bus. Okay. For a 32-bit address bus, that essentially goes from 0 hex, right? I am going to drop this h as we move forward. Keep in mind that any time I am writing an address, invariably I mean hexadecimal, because programmers typically think more easily in hexadecimal. It's much easier to understand an address space when we are talking about hexadecimal. Why? Because it makes a lot of the sort of sub-memory calculations, etc., a lot easier. Okay? So, in general, when I am talking about memory blocks, it's going to be in hexadecimal, right? It starts from 0, and for a 32-bit bus, the highest possible address is all Fs, right? Of course, there is also the question of whether the 32-bit address value is being treated as signed or unsigned, etc. It does not matter, right? What is interesting over here is this 512 MB of DRAM that I have is obviously not occupying this entire 32-bit address space, because 32 bits corresponds to 4 billion elements, right, 4 gig locations, right, whereas I am talking about only 512 M locations. So, what I can do is I can take this and map it into some portion of my actual address space, right. So, this corresponds to so called physical memory, right. In other words, if I try accessing, if I have a pointer and the value that I give that pointer is some number which lies between these two values, it corresponds to something which is in the actual physical memory of the system, right. What I can do therefore is, what happens to all the other memory locations? Right now nothing. If the CPU tries to read from some memory location which is outside of the physical range, it will probably result in something called a bus error, right, where the operating system will basically say, I do not know what to do with this, right, or if there is no operating system, if you are lucky, you will just return without any meaningful data. If you are unlucky, the system will crash, okay. But what that means is there are now a whole lot of addresses that do not have any physical meaning. What I will do is I will take some of them and map this hardware accelerator onto that, okay. So, what does that mean? When you go through the process of actually creating a module in Vivado, which is next, right, we will find that the numbers that are assigned over here are typically something like this. There will be some 4 followed by all zeros, and some upper limit which is again this 4000 followed by, let us say, FFFF, okay. Effectively what it is saying is any address in this range 4000 up to 4000 FFFF corresponds to this particular hardware accelerator. If I had another hardware accelerator, it would go into another range of the memory, okay. Now what happens? Let us say that the CPU generates the bus address, right, the address which is given to the bus is 4000, okay. What should I do with it? I can't really read anything from that memory location directly, but the bus can now figure out that, okay, this particular thing corresponds to where this hardware accelerator has been connected, okay. But the hardware accelerator by itself does not need to have all the 32 bits of the address. It does not have a 32-bit address space. The hardware accelerator has been designed with, according to what I have drawn over here, this is only a 16-bit address, right, because it corresponds to 0000 up to FFFF, right, that is 16 bits of address. So, the bus can basically remove the first 16 bits. Once it decodes the first 16 bits to be 4000, it will remove those first 16 bits, send the remaining 16 bits to the hardware accelerator along with a select signal that says you are up, respond, basically a chip enable signal. That is what happens in practice, right. The bus takes care of decoding the hardware address and sending a subset of that address to the hardware accelerator, What's the advantage of that? Once this hardware accelerator receives that smaller address, which is the 16-bit address, it need not be 16-bit, it could be like 1 bit, 2 bit. I can choose how many bits I want for the hardware accelerator, right? Only that many bits will be sent from the bus to the hardware accelerator. The hardware accelerator then just has to look at those, decide what to do with it, and respond accordingly, right? And that is actually interesting. Now the hardware accelerator can respond in any way that you like, because you can write logic over there. A memory has a very specific way of responding. If I give it an address, it has to go look in that particular location and give me back what was written there. But a general hardware accelerator can behave in any way that you like. You give it an address, it can decide, oh, you want to get some flag, or you want to get the value of some register, or you want to know the value of some counter. I'll take that value from whatever I have available to me and give it back to you. Okay? That is ultimately how the FFT module and other such hardware accelerators are going to get interfaced with the system that you are creating.